Sorry about that.
Why say you changed so much?
So what was going on today?
I have no idea.
Yeah, where'd you
I
go?
was trying to log in with my computer and it wouldn't accept the password.
Even for this one?
Yeah, I just had to
Or are you
I just
gonna
downloaded
say
Zoom on
no
my phone, do it on
more?
my phone, and I clicked on it and
Are
it
you
immediately
ready for
opened.
the first
I'm sorry. I don't know. It was weird when I went on there. It like won't let me unclick password like I usually do. So it's requiring one now. Like it has to
word?
have one. I don't know why.
It's okay. It's weird.
It is weird. All right. Well, I'm going to start over since no one was here anyway. So what I was saying was initially I had thought we would do module 14 for this week and next week and kind of end there, but I've changed my mind. What I'm going to do is as much of module 14 as I can this week, and then next week or for homework this weekend you'll have like a practice final, and then next week we're going to cover it and have our actual final exam next week. And module 14, 15, and 16 will not be on the final. So
Worrying about all kinds of
kind of the plan for the last 2 weeks.
Okay.
I haven't graded your test. I'll do that today, and I'll kind of like let you know about that. And depending on how that went for everyone that turned one in, we might spend some time on that. So we'll just see. All right, well, we are going to start module 14 now. So page 492.
Number 2.
And last module, we talked about whether or not reactions can occur spontaneously. And that was based on our thermodynamic criteria. So enthalpy, entropy, all that kind of stuff. And this module called kinetics is going to speak to how quickly reactions proceed. So again, I'm on page 492, and they give you an example here. So that equation that you see there is the decomposition of hydrogen peroxide. So your reactant is the hydrogen peroxide, and it's breaking down into water and oxygen gas. The standard Gibbs free energy for this reaction is negative 190 kilojoules per mole. So that means the reaction is spontaneous since it's negative. But if you watched hydrogen peroxide sitting in a glass all day, you would never see bubbles of oxygen being produced. And that's why you can have it sitting on a shelf for years and it's still just as good as it was before. The reason being, the reaction is occurring very, very slowly. So yes, it's spontaneous, but it's occurring really slowly. So it's good to know how quickly or how slowly reactions are going to occur, because otherwise there's no point in like observing them. So that's kind of what we're learning about this module. So even if it's spontaneous, if it doesn't proceed quickly enough, there's no point in running it. So we're going to talk about a couple different things today that affect the reaction rate of a reaction. And we're going to watch, there is an experiment, and we're going to watch like a little clip of it. Just because it's easier. Someone else has done it on YouTube, and we'll kind of watch it together and talk about it. So first, we're going to talk about reaction rate. That is the rate of change of a product in a chemical reaction. So basically, how quickly your product is being produced. And in mathematical terms, you'll see your equation there on page 493. It's equation 14.1. And that is, we're going to break it down. So your capital R stands for your reaction rate. And as you know, the delta, the little triangle, means change in. And you see product and reactant are in these brackets. And that just means concentration. You remember we talked about concentration a couple modules ago. So the change in concentration of your product divided by the change in time, T is time, or it can be the negative change in concentration of your reactant over change in time. So one or the other, they're the same. So let's see. The unit that we're going to use, usually we're going to use molarity for concentration, as we talked about before, and then your time is usually going to be in seconds. So it would be capital M over S, molarity per second. That's the unit for the rate of a chemical reaction. And just briefly to talk about the negative sign for the second equation that you have there, the reason that it's negative is because products are being made. So that's why the product one is positive. But when in a chemical reaction, the reactants are being used up. So that's why it's a negative sign there, because your reactants are being used up. So the negative sign kind of balances out the decrease that's going on there. So just know that you can do either of those. So as long as you know one or the other, you can use either of those equations to calculate that. And now let's get to the factors that are going to affect the rate. So questions that we're going to answer are, if a reaction is slow, is there any way that we can speed it up? And alternatively, if it is occurring too rapidly, is there a way to slow it down? So let me pull up here. Let's see. I've never done this before, so I'm going to try it. Okay. I'm going to pull up the experiment we're going to watch. Sorry for whatever pops up on my YouTube. I don't know. Let's see. Okay. And I saved it. It was kind of cool because I know it's a weird video, but she is actually doing it directly from the same book we are.
Hey, chemistry.
So I'm just going to fast forward.
Get ready for lab number 14.
First of all, I want to explain. This is experiment 14.1, and I'm just going to explain what she's doing so that we can save all that time that she wastes talking about it. Basically, she's going to put, you see the Works toilet bowl cleaner behind her, and we used toilet bowl cleaner for some of our other experiments. It's corrosive. So she's going to put a small amount in 4 different jars. Our first jar is going to be our control. So it just has toilet bowl cleaner in it. All of the jars are going to have the same amount. So the first jar just has toilet bowl cleaner, and then she's going to have antacid tablets, and she's going to drop those into the containers of toilet bowl cleaner. So the first one is going to be the control, the first jar, and that's just toilet bowl cleaner with nothing added, nothing different, with the antacid tablet dropped in it, and we're going to see how quickly that antacid tablet dissolves. The second jar is going to have the antacid tablet crushed up, so it's like powder form now instead of a solid chunk, and that's going to be in the second one. The third one she's going to heat up, so it's going to be a hot toilet bowl cleaner with the antacid tablet, not crushed up. And then the fourth one is going to be a diluted toilet bowl cleaner with the chunk of tablet put inside of it. So let's fast forward. Let's see. I went to this part, and we'll see what kind of happened when she did all the things. And I think she let it sit for 5 minutes, which is what you were supposed to do, and see how much was dissolved.
All right, that was our 5 minutes. Now, what we have is our number 1, which is, we'll call it control, because we know how much toilet bowl cleaner was in there and how much antacid was in there. We're going to compare it to number 2. Okay, that's the first thing we're going to do is our control test tube 1 versus our experiment number 2. Now, what is the difference? They both have the same amount of toilet bowl cleaner in them. Everything sat for the same amount of 5 minutes. The difference is this was a solid chunk of antacid and this was powdered. So let's take a look inside. Okay, so what we have here, you can see there is still a good sized chunk of antacid in there. And then we're going to look over here in this one where the powdered stuff was. And we see, I don't know if you can see it real well, there's a little bit of residue in there, but no, these are great test tubes. There is some residue in here, but not very much. So I would say that powdered chemicals increase the rate of chemical reactions. Okay, if one is powdered, it's more easily dissolved into the liquid. Okay, that's what I've learned from this experiment, 1 versus 2. Let's take number 2 out of the equation and let's look at number 3. All right, and if you remember, number 3 was hot. We have the same amount of liquid, the same amount of hydrochloric acid, the same amount of toilet bowl cleaner, and we added to each of them a solid 1/4 chunk of antacid. Remember, they look a little different. It's the size, it's the glass, it's whatever, okay? Let's look inside of them and see how much is left. So this is number one. You just saw this a moment ago. You see there's a good sized chunk of antacid. It's smaller than it started, but it's still pretty much there. Now, if you remember, this was the warm toilet bowl cleaner. I put this on the stovetop in some warm water and heated it right up. So what do you see? We have changed what? We didn't change our antacid like we did in number two. We've changed the temperature of our chemical reaction. And what do we see? When we have increased the temperature of our chemical reaction, the reaction rate increased. Okay, that's what we saw.
Powdered and hot.
Well, thank you for jumping ahead, Zeke.
Oh, I'm supposed to not do
No,
that.
you're fine. Just keep your mouth closed. All right, so let's move on to number three, or third, well, number four, our third comparison. So again, toilet bowl cleaner, antacid. We have the same amount of antacid in here. The difference we had here is less of our toilet bowl cleaner. Okay, so what we have is our 100%. We'll call it 100% concentration of toilet bowl cleaner, and then a 1/4 concentration of toilet bowl cleaner. And I'm sure you can make a guess, or I'm sorry, I'm sure you can make a hypothesis here. Let's look in here. So we have a good sized chunk still left, and actually still some bubbles. And this one also has a good sized chunk, like hardly any bubbles. Okay, the bubbles are the carbon dioxide for me. That's actually our chemical. No, that's just for me shaking it. Okay, so I would say, like, not much happened. And that is because of the chemical dilution here in test tube number 4, because it was diluted. So if we dilute something, one of our chemicals, it slows down the rate of reaction. If we increase temperature of one of our chemicals, it will increase the rate of reaction. And if we increase the surface area of one of our chemicals, okay, the antacid tablet was powdered, so it had more surface area to react with things, it will increase. So increasing surface area increases your rate of reaction. Increasing temperature increases your rate of reaction. And reducing dilution will reduce your rate of reaction. So number one.
All right, that's the only part that I wanted us to watch. So let's go back here. How do I unshare my screen? Okay. Anybody know? Okay, stop share. Okay, got it. Okay, so that's the experiment that we would have done had you guys been in class. Hi, Marshall. So we'll kind of talk about what happened there. So I'm going to go ahead and turn over to page 496. This is what we call a controlled experiment. So you had your control, which was the one with just the toilet bowl cleaner, nothing was changed, and your tablet was put in there just as is. As you saw, it did start to kind of break down the antacid. There were some bubbles happening, but there was still a pretty good chunk in there. With the number 2 jar, she crushed it up so that it was a powder. And as we can say, you know what surface area is from math class, I hope. So you have a chunk, that's a pretty small surface area. If you mash it out into a powder, it's going to be, you know, a larger surface area. So increasing surface area of the chemical is going to increase your rate of reaction because it was all the way dissolved pretty much. And then the third one was heated up. So when you heat up a chemical, it increased the rate of reaction because it was more dissolved. There was still a little chunk, but it was more dissolved than the control. And then fourth, we talked about concentration, or third, we talked about concentration. So the diluted version of the toilet bowl cleaner was a slower reacting. So in other words, we can flop that, and increasing concentration of a chemical would increase your rate of reaction. So let's kind of talk about why all these things affect our rate of reaction. As we talked about before in module 3, the valence electrons of an atom are what are responsible for the chemical behavior. And in module 4, we learned that in order for them to transfer valence electrons or share valence electrons, they have to get close enough to each other, the atoms. So if you think about it, first of all, we'll talk about the powder. So if you think about you're spreading out the atoms versus being in a small chunk, When you spread them out, they're more likely to collide with each other and react together. So it makes sense that it would speed up the rate of reaction because they're spread out, they're going to run into each other more. The atoms are going to react together more than if they were in a small little chunk like that. Temperature, if you think about that, when you heat up atoms, they're going to move faster, right? The colder something is, the less it's moving. The hotter it is, the faster they're moving, the more they're going to collide, the more they're going to react. And then third, the concentration, that tells us how many molecules are in that substance. So if you increase the concentration, you have the same volume, but more of those atoms in there, there's more atoms to run into each other. So that should make sense too. So do pay attention on page 496 and 497 to the blue statements. That's telling you to react, chemicals must collide with one another, so their electrons can either be transferred or rearranged, like I said in the beginning. Number 2, at the bottom of 496, higher temperature increases chemical reaction rate because the molecules are moving faster, increasing the chance for a collision. On page 497, you can go both ways with this one, but we'll talk about decreasing like they did in the experiment. So decreasing concentration or diluting something decreases the chemical reaction rate because there are fewer reactant molecules to collide with one another. And then surface area, the last blue statement, increasing the surface area of a reactant increases the reaction rate because the molecules can more easily mingle with the molecules of the other reactants. So in the end, in summary, the major factors affecting the rate of a chemical reaction can be understood in collisions. So in the amount of times they're going to run into each other, because that's how valence electrons are rearranged, are shared, are transferred, and that's how chemical reactions occur. So collisions is the main thing you want to remember there. Now, all we're going to do is go over 14.1 and 14.2 on your own. So if you want to get your student book out. Sorry, I was not on that page yet. Okay. So the first question on your own, 14.1, says 2 containers are filled with the same mass of both nitrogen and hydrogen gas. If the first container is significantly larger than the second, in which container will the reaction be fastest? So 2 containers have the same amount of nitrogen and hydrogen gas, but one container, the first one, is way bigger than the second container. So which one do you think will have the faster chemical reaction?
The smaller one?
Yes, so the second container. Good job. And 14.2 says the muscles in an animal's body are run by chemical reactions. When these reactions occur, they contract the muscle, making it move. A biologist is studying the lizard and notices that when the lizard is in a cold place, it moves very slowly. But when it's in a warm place, it moves very quickly. Explain this observation in terms of physical kinetics.
Seizure.
Any ideas?
When the muscles are warm, they're more active.
Yeah. So the higher the temperature, just like we said, the higher the temperature, the higher your reaction rate. Same thing in your muscles because chemical reactions are occurring in your muscles. So higher temperature, higher reaction rate for muscles. This is a pretty easy section. We technically could move on, but I think I'm just going to call it a day. And then we'll do some more tomorrow on the math side of things.
Okay.
And I'll read your test and let you know how that went and what I'm going to do with that. Did you have any specific questions you want to ask me before we end class?
What were you saying at the beginning?
Yeah.
For the final?
Yes. So I'm going to do as much as I can for module 14 this week. So we'll do all module 14. For homework, you're going to get a practice final exam,
Okay.
and we'll go over it Monday and Tuesday.
Alright, so the two that I'm
And then
looking
Wednesday, we're
for
going to have an actual final exam.
are the crossword puzzle and
Now,
the,
module 14, 15, and 16 are not going to be on your final.
excellent.
Okay.
Let's do the crossword puzzle first.
So after the final, we're not going to do anything else?
Number
That's the last day of classes next Wednesday. So
Okay, yeah. It's the 20th, right?
Yep.
Or the 22nd?
the 20th, yeah.
Reagan.
Okay.
Close to the end.
You haven't done your work yet, Sasha?
Anybody else? We good? Okay. Well, let me know if you need anything before then. I'll send you your grades as soon as I'm done.
Okay. Don't
Alright.
be surprised if it's low.
Okay, thanks for warning me. See y'all tomorrow.
Well, then I guess you guys can just listen.